Hello. Now we will learn the combination of capacitor. So first combination we'll learn is a series combination. So we are having two capacitors of capacitance C1 and C2. And we have joined these two capacitors in series. Series means one end of a capacitor will be joined directly to the other end. Okay, so these are the two capacitors, they are connected in series. So when two capacitors are connected in series, they tend to carry the same charge because ultimately they are a part of a single structure, single wire. So if they are a part of a single wire, whatever charge will flow onto this plate, the same charge will go at the other end. So they'll be having the same charge. So here I'm writing plus Q, here it will be minus Q, here it will be plus Q, and here it will be minus Q. So that is the charge. Same charge will be there in each and every capacitor when they're connected in series. And we want to calculate the effective capacitance of this whole structure. So what I'll do, this whole structure I'll define by single capacitor, which will be having the same charge as the charge earlier. Basically, the A and C point will be same point. So the potential difference across A and C point I'll not be changing. All I'll do, I'll replace the structure by a single capacitor, which will be having the capacitance C effective. And I want to calculate the value of C effective. Okay. Now, for that, what I'll do, I'll calculate the potential difference between each and every capacitor which is connected in series. So the first thing is I want to calculate VA minus VB. The potential difference between these 2 points will be equals to charge upon the capacitor divided by capacitance of the capacitor, which will be Q1 upon C1. That is my equation 1. Now I'll do the same thing, meaning I'll calculate the potential difference between these two and B and C. So VB minus VC. And as you can see, this B point is connected to the positive charge, so obviously it is going to have the higher potential. So it will be equals to Q1 divided by C2. Oh, this is Q. I've taken this Q actually. If I add these two equations, meaning if I add equation 1 plus equation 2, we'll get VA minus VC, and that will be equals to, I'll take Q common, 1 upon C1 plus 1 upon C2. That I'm saying equation 3. So this is the final equation for the above structure when there are two capacitors connected in series. Now I'll make the same equation, I'll calculate the value of potential difference across this A and C point, but using this structure, second structure, the final structure. So in this case, if I use this structure of the capacitor, VA minus VC will be equals to charge onto the capacitor divided by capacitance, which is C effective. This is. Now we are saying that both of these structures are same structure. If that's the case, so you see the potential left hand side is same for both the equation, charge is same for both the structure, so the remaining things should be same also. So if I compare between equation 3 and 4, I'll get 1 upon C effective is equals to 1 upon C1 plus 1 upon C2. Okay. So this becomes the value of the C effective value. This becomes the value of effective capacitance when they're connected in series. Now here we have taken two capacitors in series. So what if we are having n number of capacitors in series? If I'm having n number of capacitors in series, and if I want to replace this structure by a single capacitor, C effective, then applying the same formula, we can say that 1 upon C effective will be equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3, and this will go on till 1 upon Cn, whatever is the value of Cn. Okay. So that becomes the formula. This is the formula for combination of capacitors when they're connected in series. This formula one should always memorize. So whenever we'll see multiple capacitors connected in series, we will be simplifying those structures and we'll be replacing those structures by single capacitors. Okay, it will be easy for us to calculate from that way. Okay, thank you.